Hello, welcome to Math 204, part of the University of Wollongong's Complex Variables Mathematics degree. Math 204. For those of you following along at home and perhaps paying any kind of attention, I also happen to be teaching Math 321, and this is being recorded directly after I've done rather a long session of talking about Math 321, so please excuse silliness. Not that maybe smiley faces are particularly silly. I tried to practice drawing a cat. Yeah, it's not pretty, right? Yeah. Anyway, section 2.3. Right, what are we talking about? Polynomials and rational functions. Definition. A function P from the complex numbers to the complex numbers is polynomial if it can be written as pz equals a d zd plus a d minus 1 zd minus 1 plus a1 z plus a0, for d an element of the natural numbers union 0, because we're not considering 0 to be in our natural numbers in this class, as I have just discovered, and a d minus 1 down to a0 inside the complex numbers. Polynomial, complex bits. The powers have to be natural numbers, so no weird powery stuff going on here. Okay. The largest d, so that a d is not equal to 0, is called the degree of p. Note, I have not said that these things have to be non-zero. Just in C. C contains 0. These things can be 0. In particular, AD can be 0, in which case this polynomial might be degree d minus 1. Maybe. That's why it's defined, the degree is defined in this particular way. P is monic if a d equals 1. So the highest degree has is equal to 1. The coefficient in front of the highest degree term is equal to 1. P is linear. D is less than or equal to 1. So in particular it includes constant functions as well as functions with a constant slope. Fundamental theorem of algebra, which we still have not proven, implies that there exists alpha 0, alpha d, in this case I do require the degree to be equal to d. That one has to be non-zero. I have not necessarily written that particularly the best way, but anyway. Yeah, and not necessarily distinct. This particular decomposition is unique. These roots are unique. Every polynomial has, those roots don't change, right? So that decomposition is unique. Or maybe I should say the factoring. Well, is it unique? It's unique up to a reordering of the roots. Sometimes that matters, sometimes it doesn't. alpha 1, alpha d are the zeros of the polynomial, also sometimes called roots. Alpha I is a0 and is of order h if exactly h zeros are equal to alpha I, sometimes also called the multiplicity. This is a cool little result because this is false for the real numbers. And suspiciously, or maybe not, it's kind of related to the square root one. Let p complex numbers to the complex number be a polynomial of degree at least 1. So that's to ensure that we have at least one root. And w, an element of C, arbitrary. Then w is inside the range of p, i.e. there exists z, an element of the complex numbers, so that p of z equals w. Now, before I give you the proof, this is not true for reals, so let's consider the function f that takes x to x squared, and we're considering this inside the reals. We can draw this. Okay, any element inside the codomain. Codomain is R. Here's an element, -1. This claim is that that is always inside the range, but here, -1 is not in the range of f. Why is that? Well, because there's no natural number whose square is -1. So, this is related to the fundamental theorem of algebra, which is related to the very definition of the complex numbers. It's a kind of a cool little fundamental result, that little lemma. The proof. How does this work? Well, p is a polynomial, so I'm going to write this out. AD, ZD, all the way down to A0. I can write a new polynomial. Let's have Q, Z is equal to A, D, ZD plus all the way down to A0, and I'm going to chuck in minus W, because W is a fixed thing, so good. QZ has a root, so there exists alpha. Sorry. Great. Well, what's this thing? This can be written as P of Z minus W. So Q of alpha is equal to P of alpha minus W, which is equal to 0. So P of alpha equals W, and we're done. Great. Another lemma. Every polynomial is continuous. Proof. Perhaps not very surprising, because the same is true in the real numbers. We know that the function 1 that goes from the complex numbers to the complex numbers, that takes z to the number 1, and the function which I've been calling iota z to z, which takes z to z, are both continuous. we also know that if f and g are continuous, then fg and f plus g are continuous. Now here's the claim. Every polynomial is built from sums of products of the functions 1 and iota. Therefore, every polynomial is continuous. Why is this true? That's left for you. Please think about it. It's an interesting result. Why is it interesting? It's interesting because while the particular proof seems very obvious and clear, this approach where you prove results for certain functions where things are very easy, and then show that other functions are built from those functions and therefore must satisfy certain properties, like continuity, is a typical approach in mathematics. When you get a little further on, you'll see this happening again and again, and so that's why it's worth having a think about this. Another definition. A function R from C to C is rational. It's a rational function if there exists P, Q polynomials so that R of Z is equal to P of Z divided by Q of Z. Always, there's one assumption we always make about this. Always assume that P and Q have no roots in common. What if they did? If they did, then the factorization would mean that there was a factor on top that was the same as the factor below, and we could cancel them out. So we always assume that P and Q are somehow minimal. Wow, that looks really bad, somehow minimal. Anyway, so no roots in common, which is important. Right, this implies that 0 over 0 never happens. Of course, dividing by 0 means that the rational function is not well defined. Now, you can extend the rational function into so R from C to C rational can be extended. Let me say this: the C union the point at infinity, and then say we can define R of Z equal to the limit of W goes to Z of R of W, which will equal infinity whenever Q of Z is equal to 0. So as W approaches Z, the quotient will get very small, the denominator remains bounded, and we define the limit to be infinity, which is why I've put infinity in there, and why I have not removed the points from the domain where Q has roots. If I did not want to put infinity in my codomain, then I would need to remove the points where Q was 0 from my domain. Well, I haven't done that. Infinity has to be in the codomain, and we define the function to have the value infinity where Q is 0. And that's fine because the value of P at any point inside the complex numbers will be bounded. bounded number divided by something that is getting very small will be something that tends to infinity. And you can check actually that this limit does actually go to infinity based upon the definitions you've seen already. Okay. R from C to C union infinity can be extended to a function that I'll also call R from C union infinity into C union infinity. By defining R at infinity is equal to the limit as z goes to infinity of R of z. We know how to work out this limit. That's what that is. And the reason why the limit is well defined is basically related to the fact that we're working with polynomials here. Polynomials are really nice functions. You should prove that the limit exists. If you actually did all of the exercises and things that the things that I'm leaving left out in the notes, your education for complex variables would be quite good, and you should be able to pass the exam, the mid-semester tests, and the assignments easily. So you should do them, right? Of course you should. Oh, of course you should. It's not just because I'm a lecturer and have a vested interest in you doing well. Certainly not. Okay. That's it. That's it for section 2.3. Okay, thanks.